So I would like to acknowledge my many, many collaborators without whom this work would not be possible. Spiro is obviously my advisor. I work very closely with Rick DeVore and Judy Carpin. The code that I'm using for all of this stuff was written by Kai Jermashevsky at University of New Hampshire. And I collaborate with Naoki Besho. All of the Pulsar work has been done with Alice Harding, Kostas, who I'm not going to try to butcher his last name, Dimos Kazanis, and Andrei Timokin. They're all sit at Goddard and have different institutions that they're employed by. So everybody should be pretty familiar with this beautiful image of the sun. This is a picture of a pulsar, the Vela pulsar. I don't remember exactly where it is, but it's pretty. It shows the emissions, and it's swirly and lovely. Okay, so here's a quick outline of my studies. I'm going to talk a little bit about reconnection, magnetic reconnection, and kinetics. We'll go into the details of the numerical model that I'm using, so please ask me lots of questions about the numerics. Then I'll discuss a little motivation from different stellar magnetospheres. And then this is broken up into two different projects that I'm working on. One is on pulsar magnetospheres, which have very different properties than the solar corona does. And then hopefully we'll have lots of time also to actually get into the kinetics of the solar corona and the problem that I'm working on there. Okay. So I'm sure we're all very familiar with magnetic reconnection. It's a fundamental process throughout the universe. We see it in the heliosphere, we see it in planetary magnetospheres, we see it in fusion devices, and then it turns out that it's probably pretty important in other stellar magnetospheres as well. So my focus obviously is kinetics. There are global consequences for reconnection that depend on kinetic scale processes for the flux breaking, right? So there's lots of work going on here on the big global picture, but we need to figure out what's happening on the very small scale and understand how that feeds back. So the long-term goal of all of this work is to do real multi-scale coupling. So really take whatever the important kinetic physics is and feed that into a big global model. That's not exactly the scope of this talk. The work's not quite there yet, but in the future we will definitely be working on this. And there are lots of people that are already working on how do we do this coupling appropriately. So as I said, we need to understand the kinetic scale flux breaking to appropriately model the global system. And that's really what I'm trying to do. So there's a lot of work in kinetic studies that involve pre-existing current sheets, so things like the Harris sheet. We love to take the Harris sheet and just perturb it and let it go, right, because this is a nice analytical equilibrium. The fact of the matter is, reality, we don't just have pre-existing current sheets. These current sheets are formed. There's not a lot of work on that. That's a more difficult problem. And so that's ultimately what I want to do, is study how the current sheets form, what important physics is happening during the formation process, and how does that impact the global system. So all of the work that's presented here is preliminary for larger coupling projects, but in very, very different plasma regimes. The heliophysical plasma, we're all familiar with, has electrons and ions. In pulsars, we have pair plasmas, so electrons and positrons, right? So same charge, same mass. And they're relativistic, so very, very different things happen. Oh, so I was going to show this, this lovely movie, which I'm sure many of you have seen, of reconnection in the corona. This was made by Judy Carpin, and it very nicely demonstrates the breakout model, which is the basis of my solar work. So we have a four-flux system. You shear the magnetic field from the center, right? Forces all of this material out, and then boom. So there goes your CME. There it is again. Okay, I'm sure you all have seen that a lot.
So the current density?
Yes, it is the current density, and the field lines are drawn on top of it. Yep. Yep. So here's just the breakout model that we just looked at. So we have this four-flux system. There's a null point here. When you shear the field, it forces material, field, etc., up towards the null point and forces it from a point into a current sheet. It breaks out into a current sheet. Okay. So my work in the solar corona is to model this null point up close and personal. Right. So what I'm actually trying to do for the breakout model is to implement this shear driver on a PIC code, which hasn't been done before. Okay. So that's reconnection for the solar corona. This is a little bit of what a pulsar magnetosphere we think looks like. So what are pulsars? Pulsars are collapsed neutron stars. They spin very, very fast. They have cones of radio emission, which are shown here. So the axis of rotation and the magnetic field axes are not aligned necessarily. They're frequently not aligned. There are ones that are aligned, but they are frequently not aligned. So the sucker spins really, really fast. You have emission of radio waves here. Also at the poles, you have the generation of paraplasmas. These plasma, the pair particles then travel along the field lines in different directions, and we'll get into all of this a little bit later. But this sort of just shows you that we have these strong current sheets, right, around these lobes, and then we have this actually denotes the location of the difference between the closed and the open field lines, right? So in the pulsar magnetosphere, the region that I model is actually outside. It's actually here, where we're all dealing with open field lines only. So no, we're not going to touch the closed stuff on the inside. Okay. So kinetics are important for both the solar and pulsar magnetospheres because the physics reach beyond what MHD can capture for the corona, and then also beyond what extended MHD can do for the pulsar case. So plasma kinetics allows you to study the internal dynamics of reconnection for both of these systems, okay, despite the fact that they're very different. So we'll go into a little bit on kinetic scale reconnection here. This was taken from Masha Kuznetsova's paper in 2007. So this is a classic reconnection picture, right? We have field lines that are oppositely directed here. This is our inflow direction, right? And then magic sort of occurs on the inside, and outflow is in this direction. So this magic that's occurring is occurring inside diffusion regions, inside the ion and electron diffusion regions, so below the scales below what the MHD can actually capture. Inside these diffusion regions, the particles become demagnetized. And so where their orbits were previously nice and gyrotropic and they just followed the field lines, they become non-gyrotropic and they kind of wander between field lines. And there are lovely images in other papers that show how they can wander between these field lines, and then eventually they somehow find their way onto the open field lines, and then the plasma finds its way out. Okay. So we still don't exactly understand how that happens, what's going on in there. How do these... Spiro loves to say, the particles become confused and they don't know what they're doing. And no, the particles know what they're doing. We just don't know what they're doing. Okay, so how do we want to do this? We want to try to do this with analytical kinetics would be just fabulous if we could actually do this with pen and paper and with the full-on Vlasov equation. Okay, so this is our wonderfully complex Vlasov equation. To solve this full system, you actually would have one of these equations for each species. So this is our distribution function, right, that has 3 velocity components and 3 spatial components. We've got our Maxwell's equations, right? Oops, tapping that thing. And then the whole system is ultimately closed by calculating densities and currents here. Okay. So this is a bear. There are Vlasov solvers that will do this numerically. For a full 3D system, this is a nightmare. It's computationally very, very difficult. So instead, another approach is to use the particle and cell method. So in this case, we're trying to represent Vlasov's equation, but rather than advancing the distribution function, we're going to advance particles individually. So you start with a population of particles that you sample from a distribution function, usually a Maxwellian is what we start with for classical plasmas. You pick out, a billion particles or a trillion particles and scatter them in your domain, right? And then we'll solve this system with Maxwell's, right, which are pretty straightforward. And then you advance the particles again. Okay, so there are questions on pick. This is a good point to ask them. This is all done on a staggered grid. So we set ourselves up with a grid, but the particles are not confined to the grid, right? They can move anywhere in the domain that they want to move. Which ultimately means if you have a particle that is, say, somewhere over here, and it feels contribution from all of those fields around the cell or that, are on the edges of the cell, you have to interpolate those values to the particle location. So that's one source of error, is that this interpolation process. The other issue is that if you want to here, say, advance your electric field, you need to calculate the current, right? Which means you need to interpolate particle weighting, right? The particle gets weighted because it doesn't sit just exactly, say, in the center of a domain. So you have multiple particles from different places, and they each have some contribution to each point on the grid. Okay.
What is the time step control restriction? The Courant condition?
The Courant condition.
Yeah, what is it for you?
Honestly?
Speed of light?
Oh, yes, speed of light. Yeah, right. Your particles can't go faster than speed of light.
I mean, the time step. So it's a good spacing divided by...
Mm-hmm. Yeah, and then times some factor to bring it down a little bit. You do actually need to scale your time as well with, it's omega CE over omega PE. So, yeah, right. You need to make sure that you're capturing the plasma frequency as well.
Is there a similar CFL in velocity space?
Ooh, that's a really good question. I don't know. Oh, I mean, they can't move. They shouldn't move. They should never have velocity faster than c. But other than that, I'm not entirely sure.
Are those collision or collisionless?
This is collisionless. It's a very good question. This code does have a collision operator in it, but at the moment I'm not implementing that. Yeah. So this is completely collisionless. Collisions are another big issue. Right?
How would a particle ever acquire a velocity faster than the speed of light?
Well, numerically, it can happen if you.
Okay.
You can have tricky.
It's law of computing.
Right. Basically.
Okay.
Murphy and Maxwell were neighbors.
Okay. So the wonderful thing about our staggered grid, which maybe many of you are familiar with, is that it means we only need to prescribe boundary conditions for the electric field. You don't have to prescribe boundary conditions for the magnetic field because that's all calculated from the electric field. So for the fields, we only have electric field boundary condition, but then you also need a boundary condition for your particles. Okay. So that's kind of 101 of PIC. Okay. The code that I'm working with is the plasma simulation code. It was written by Kai Jermashevsky and his thesis advisor, Hartmut Ruhl. It is a full 3D finite difference time domain PIC code. It's modular, which I absolutely love. It means you can pick whatever boundary conditions are there and set those at runtime, which just makes my life wonderful. It's massively parallel and has dynamic load balancing, which is really nice. Yes?
Puzzled about something. I think you said that you said you did not need boundary conditions on the magnetic field.
On the magnetic field.
Because it's determined by the electric field. I mean.
Yes, because it comes from right here.
But don't you still need spatial boundary condition? You have to, or do you start from assume a uniform field? Or what?
So at the initial condition, let's see, you do prescribe the field everywhere, including on the boundary at the initial condition. But beyond that, as you time advance, any time advancing of the magnetic field only happens through the electric field. So the electric field, you need to have a value that's in the ghost cell, so outside of the domain, right? You don't need to carry magnetic field out here, essentially.
So in the ghost cell, you impose an electric field.
That's right. Or oppose a zero electric field, or whatever is appropriate for, say, conducting wall or periodic or open boundaries, which we're trying to implement. Does that answer your question? Okay, great. So this is just one of many codes, but this thing is fabulous. It's been benchmarked against Bill Daughton's VPIC. It does pretty well. They have run it on up to 10,000 processors, with trillions of particles, which just makes me really happy, so I can do these massive, massive simulations when we get to it. Okay, so the next part of the talk is going to be on the Pulsar Magnetosphere. So this is just a diagram that shows the magnetic field lines and the cone of radio emission here. So these things are really amazing. Like I said, they have relativistic paraplasmas in the magnetospheres, and they have a strong electric field, which is so very different from the solar environment, and wonderful for a kineticist to have a strong electric field to deal with. They're extremely massive. They're small. They're really dense. They have these strong magnetic fields as well. They spin super fast. These pulses have been measured on the order of milliseconds. Yes?
I was just wondering if you're assuming a collisionless plasma,
Yes.
but for neutron stars, that's still a good assumption.
Is it still a good assumption? That's a really good question that I don't know the answer to.
I mean, for the corona, I'm happy with that, but for
It may
neutron
not
star,
actually be.
Well, she's not doing the star itself. She's doing the magnetosphere of the neutron star.
But
which
still.
is why I'm asking, what is the density up there? I really don't know. Is that the mean density of the
star?
Of the star.
Yeah.
What is it in the magnetosphere? I don't know.
Yeah,
I know it's in the corona, but
I think
I don't have a feel for it.
in the magnetosphere, I think we're still arguing about this. So what I need for parameters for input are densities and temperatures. And they say, well, but that's what we want to get out of your simulation.
Okay.
So,
Chicken and the egg.
huh?
Chicken and the egg.
Chicken and the egg, exactly. It's hard to measure the densities of these things, from so far away.
It's astrophysics. Make up a number.
I wouldn't dare. I'm being webcast here. Somebody could call me on it, right? Okay. So these things.
Make up a number.
Huh? These things. They put these, send these pulses. This is why they're called pulsars, because you can see these pulses that are on the order of milliseconds, and they are so incredibly precise. They are more precise than atomic clocks. They really are nature's timekeepers. Okay. So here's a little more on the background of the pulsar electromagnetic field. So they have these strong magnetic fields, which are rotating really, really rapidly with the star, and this generates a strong electric field. Right? So this induced electric field, the sign varies according to the magnetic field on the surface of the star. This, okay, I should say this very carefully. Pairs, electrons, positrons, are created at the poles, right? Like I discussed. They respond differently to this electric field, right? Because they're differently charged. This ultimately means that one charge dominates at the poles, and another charge dominates at the equator of the magnetosphere. So you really do have an actual charge imbalance in these magnetospheres as well, which is different from the assumptions in the corona, which are that we have a neutral, right, an overall neutral plasma.
So does that mean charge separation along a field line? Or are they still, if it's collisionless, they're still tied to the field.
The
There's still-
magnetic equator or the?
Hmm?
When you say it's along the equator, do you mean the magnetic?
I mean the magnetic equator, yes. Yes. Okay. So, charge along the field line. Yeah, okay, so I guess you would be right about that the charges would be different along a magnetic field, right? So you would have, say, more of one charge here and same charge here, but then different
Right,
charge
so the
here.
charge separation occurs along the field.
Along a field line. Okay, so current extended MHD models can't actually capture the full self-consistent electrodynamics, so we really do need a kinetics approach to solve this problem. Okay, great. Right, so here, the other thing that's kind of interesting about the pulsar magnetosphere is that there's this thing called the light cone. I don't know how they came up with this name, maybe somebody in this room knows. But it denotes the boundary between these open and closed field lines. Oh, God, I lost mine. There it is. Right. So right along here. So beyond this. So everything that I'm trying to model is beyond the light cone. Question?
I'm sorry.
Yeah.
Please. It's just very different from the sun. So
Yes.
it's you have a highly conducting plasma, but yet you've got strong electric fields and large charge separation.
Right.
It's just very.
It's very different. It's very different. It's wild. So everybody should be fairly familiar with a plot like this. This came from Uzdensky and Spitkovsky, which just came out this year. They have hypothesized that there are reconnecting plasmoid chains out here in the current sheet beyond the light cone. So this is essentially what I'm trying to model, is what are the kinetic effects in this regime, in this area. Okay, so we have this grand vision for this big project, right? We're going to start by implementing a kinetic equilibrium that has a strong electric field. This would be brand new. Nobody's done this before. And then we want to drive this equilibrium to reconnect, examine the energy budget. And then ultimately, we want to study the current sheet formation rather than just assuming this pre-existing Harris sheet and identify the critical mechanisms in current sheet formation. But all I'm going to show at this point is what a kinetic equilibrium with a strong electric field actually looks like. Okay. So we are doing a modification on a Harris sheet. The Harris sheet we love to study because it's an exact kinetic equilibrium, and we have very few of those. But it assumes we have this infinitely long current sheet. The magnetic field, the magnetic pressure and the thermal pressure are in balance. We have a well-prescribed current. We've got a nice analytical, we've got a nice equation for our magnetic field. In the kinetic models, you have a stationary Maxwellian distribution with no spatial variation. That's a background population. So you have a background population of electrons, and in this case, positrons. Well, electrons and ions, right? If you do the classical Harris, it's electrons and ions. And then you have a current carrying distribution on top of that that has a spatial variation, a spatially varying density. And that's our N1. Now, typically in kinetic models, you have a large background population and a relatively small current carrying population. And so this is nice and stays in equilibrium, even in the noisy PIC calculations. But Besho and Bhattacharjee did some work with a low background population, and they show that actually due to the fluctuations in the PIC codes, this is unstable to nonlinear tearing, so you get island formation naturally. Yes.
So is the rotation an important factor here? I would imagine the normal, or the original Harris current sheet was, it was not rotating.
It was not rotating.
But in a neutron star,
In
it's
a
very rapidly rotating.
In a neutron star, it's very rapidly rotating. So we're sort of assuming that we're going to ignore major rotation effects except for the electric field and the charge separation. Other than that, if there's anything beyond that, we're choosing to ignore it.
Like centrifugal forces are not.
We're not,
Okay.
yeah, no, we're not considering any of that. Just for cleanliness.
But it's also very small scale, so. And
It is small scale.
scales, well,
These things are spinning really fast. You could see that there might be.
In fact, I was wondering, is the definition of the light cone, which you said you weren't quite sure of, is that where the rotation speed gets up to the speed of light? You know, at that distance where you're,
Yes.
okay.
But
so,
yeah.
all right.
You just triggered something there for me.
Okay.
Yes, there is something, right, along those lines. I think there's something to do with the models for the inside and the outside and the matching them right at that region too. That's all done by those astrophysicists. Okay, so Rick DeVore recently re-derived, if you will, Harris's solution without dropping the electric field. He presented this recently at the AAS meeting in January, and will be presenting this at the SPD meeting. So if you folks are coming, please do come. I will also have my poster on this work. Come talk to us about it. In this case, we have a pressure balance of thermal, magnetic, and electric forces. Yeah. So you have to do this numerically. You can't do this analytically. And in this case, you can't actually have a background population because all of the particles will just respond to the electric field. So you don't keep this nice thermal population that's kind of ignoring everything that's going on. They all respond to the electric field. So that's a little bit different. So Rick wrote this code that gives us a solution for this electrified Harris, and then given the drift velocity, the temperature, and the charge imbalance, we get electric fields, magnetic fields, and charge density profiles. And then I read those directly into my PIC code and use those as an initial condition. Okay. So this is what we've got so far. So this is a benchmark of a relativistic, semi-relativistic Harris sheet, charge neutral, but pair plasma, right? So electron mass is equal to ion mass, and their charges are the same. Now, I say this semi-relativistic because the astrophysicists looked at this and said, oh, you're only at 0.5, your drift speed is only 0.5 C. Like, that's not very fast. It needs to be like 0.999 C or something like that. Oh, geez, we'll get there. Parameter space here, people, right? So let's see, the temperature was about 4 times the rest energy. Current sheet half width is 4 electron skin depths. And for this particular set of circumstances, 1 Debye length is half of a, 1 electron skin depth is half of a Debye length. So there's something very interesting that can happen with the relativistic plasmas, which are that the Debye length can actually be larger than a skin depth. If your temperature goes up enough, the regimes flip, which is fascinating and strange all at the same time. So we chose a box that was, relatively small, 30 electron skin depths in one direction and 100 in the other, and just killed it with spatial resolution, and ran about 400 particles per cell per species. So in a single cell, we're talking 800 particles. So just for comparison, marginally, we do test runs that are like 50 particles per cell per species. The statistics are not fantastic on that. Ultimately, we'd like to have thousands of particles per cell, but computational resources and such limit this a little bit. For this particular case, we ran conducting wall, so closed in one direction, and periodic in the outflow direction. Okay, so these are just the profiles that were read into the PIC code. Pretty straightforward. We've got our hyperbolic tangent magnetic field, right? And that's what our lovely initial condition looks like. So the conducting wall are here and here, and these are periodic conditions.
Is there an imbalance between electrons and positrons?
No, in this one it's completely neutral. So we thought we would just do a test case with neutral plasma, no electric field, 0 background population. You know, make sure that our code is working like Besho and Bhattacharjee suggest it should. So we see not too long into the simulation, about 12 alphane times, we start to see our first reconnection. First reconnection is a little ambiguous, but the field lines that I drew reconnected. Okay, so ultimately it breaks up into these islands, which we expect. So looks like we're in the ballpark. Probably the code's working right. So the next step was to actually go on to do charge imbalance, strong electric field case. Okay. So we still have a profile magnetic field profile that looks like a hyperbolic tangent, but it's not exactly. And this is what our electric field profile looks like. Okay. So let me just show you. So the electric field is actually strong here and negatively strong here, right? And then goes from one side to the next through the current sheet. Okay. So that's what this profile is. Okay. So at the very center of the current sheet, there is actually a charge imbalance. This charge imbalance is what was prescribed to Rick's codes. Okay. But it does this lobe-like behavior where the charge imbalance is actually stronger just outside the current sheet, or just at the edges of the current sheet. So those are our profiles, our initial condition, and this is our time of first reconnection, which is pretty close to actually the charge neutral case. So instead of 17 alphane times, we're at like 12.5 alphane times, which was kind of interesting. And then our islands form, and that looks pretty much like the classical Harris case. So that's nice. It's a first step. It's unstable to the nonlinear tearing mode. This net charge equilibrium is unstable to the nonlinear tearing mode. But we need to do several more cases. We need to run something with a larger charge separation. That electric field is not even close to what they think the electric field should be like in the pulsar magnetosphere. Although getting an estimate on what they think it should be like has been very much of a challenge. We know it shouldn't be this weak. The charge separation should be much stronger than like 1% or whatever it was that we did in this particular run. So that's what we're working towards, is larger charge separation, higher temperatures, and higher drift speeds. So charge separation and drift speed are related.
Is that the results depend in any way on the rotation speed of the pulsar, or is it
I'm certain that it does. It must. The details of it I couldn't tell you from knowledge. I can just tell you from kind of intuition. I think that maybe the faster the thing is spinning, the stronger your electric field is, the more likely, the larger your charge separation is going to be. Yeah, I think that's the way to think about it. So if they're slower, weaker electric.
There is an implied rotation rate when you talk about a charge separation.
I'm sorry?
There is a sort of an implied rotation rate when you talk about a certain.
Yes. Yeah. Okay. So beyond this, once we've done these nice cases with this electrified Harris sheet in a more appropriate parameter regime for the pulsar magnetosphere, then we'll work on driving reconnection by perturbing this net charge Harris sheet configuration. So we'll essentially do the typical Harris calculations with a small perturbation, except that we'll have this strong electric field and this charge imbalance. And that'll be interesting. I'm looking forward to getting to that. ultimately, the whole goal of this, again, is to understand kinetic reconnection in a pulsar. So pulsars have these things that they call pulsar flares, and the astrophysicists think that these things are impacted by reconnections. They're similar to the solar flares that we're familiar with. But I don't know a whole lot about them, but it sounds like an interesting concept. Okay. So that basically wraps up my bit on pulsars. Folks have any other questions on that before we move on?
So I have a question about boundary conditions for
Mm, mhm.
particles. I mean, reconnection is there's an inflow and there's an ejected particle, outflow, right?
Mhm.
So mass constantly, mass has to flow in and out. So
yeah.
your particles are conserved, right? And
Yep.
how do you keep them? I mean, I just you let new particles come in and let them go out.
No, for this case, the periodic boundary conditions mean that anything that comes out comes back in the other side. And anything that hits one of these, the upper or the lower boundary, just bounces off. So they just reflect.
Okay.
So this is different from the full real system. And PSC doesn't have open boundary conditions, which would feed in particles.
Because that tells you how fast reconnection is, right? So that
Right.
if the inflow would reach, out here.
Right.
Okay.
Right. It's a good
I was a
question.
bit confused on the distinction between charge imbalance and charge separation. So there's the total number, so you can have just, if the total number of electrons and positrons in the box is the same, then it's balanced, but you can have a charge separation.
Okay.
So is the box, does it have a net charge in the box or not?
Yeah, thank you. My slide is wrong. There is a net charge imbalance.
Okay.
There are more positrons than electrons
Okay.
in this simulation. Yeah, right. It's not clear to me actually that the pulsar magnetosphere is actually charge neutral overall. It may not be. Okay, good question, good question.
Well, you do have a divergence of the electric field because it changes sign, so
sign.
you have to have
You have to have charge
charge
imbalance.
yeah.
When you say charge imbalance, you said something about species before. I'm wondering what other, do you have protons in this simulation as well?
Protons. No, just in this case, we're doing just positrons and electrons.
Okay.
So no protons. And the masses are, of course, not at anything close to real masses, right? We set them to 1. No, if you do real masses or try to do real masses in a PIC code, it slows your timescales amazingly beyond maybe what. It slows your timescales, right? PIC codes are only good to out to a certain point anyway in time, so it can be very challenging to do a real mass system. Yeah. Okay. All right. Good, good. Okay. So now we get to our star, our home. Okay. So we talked about breakout already. There's a slow buildup of energy, this magnetic shear. It leads to this large-scale explosive release of energy. It's triggered by some microphysical process that we're not entirely clear on how this actually works, and it's localized in a region. It's localized in the current sheet. For accurate modeling of heliophysical events, we really need to understand what's happening on the kinetic scale. Your SEPs and such, you're not going to get that out of an MHD model. Love you all, MHD modelers, but so the MHD models simulate CME eruption on the sun with these shear magnetic fields through the core. I was going to show a sunspot evolution movie, but I'm not sure this actually helps the case for breakout, so I'll just skip it. Okay, so the numerical problem for this is to construct a 2.5D kinetic model of the X point, right? For reconnection, we're going to drive this by shearing the magnetic field out of the plane. Then we want to examine the role that kinetic waves and wave-particle interactions play in the current sheet formation, and try to determine what the critical flux breaking mechanisms actually are. So determining the primary quantities that capture the kinetic physics has been done by Masha Kuznetsova and Michael Hesse. They did this for Earth's magnetosphere. They looked at the non-gyrotropic terms of the pressure tensor and determined those were important and provided this information to the MHD modelers that were then able to correct their models. So we thought, well, that seems like a reasonable approach. We'll try to do something along those lines as well. But this Velocity-Shear driver has not actually been implemented in a PIC code previously. So the shearing of the magnetic fields is relatively simple to implement in an MHD code, and not so simple to implement in a PIC code. So MHD drives this through the flow velocity, which feeds the magnetic field. But for PIC, you can't just, give a delta V to a particle. You need to do it through an electric field. Anytime you want to do something to a particle, do it through the electric field is kind of the bottom line. So we have to set up an electric field profile that will then move the particles, which will drag the magnetic field. Okay, and we want to do this exactly on the boundary. Now this gets a little bit tricky. MHD conducting wall, closed boundaries imply that there's a current that flows through the boundary. And in a particle and cell code, you don't have current flow through the boundary unless the particles flow through the boundary. So this means you need to do open or periodic. And in this case, periodic is not an appropriate choice of a boundary condition. We don't have a periodic system. Okay. So this is a test problem. Like when I first sat down and said, oh, great, we're going to take the X point. Great, we'll just put this electric field in at the boundary. We'll let it rip and see what happens. Kind of all hell broke loose. It didn't go very nicely at all. So we said, we're going to take a few steps back and we're just going to do a horizontal field. We're not going to worry about X geometry. We're not going to worry about reconnection. We're just going to focus on what does it take to get this driver to work appropriately. So our test problem is to take, in this case, protons and electrons. Protons I use loosely because the mass ratio is 25. Right. We're going to equal temperatures. We're going to assume Maxwellian distributions. Okay, beta 0.01, so low beta plasma, conducting wall. Here's our initial conduction. So we're going to do conducting wall here. And periodic boundary conditions here and here. So a little bit suspect. Actually, now that I look at that, I think that's not right. I think we did conducting wall all the way around. I think that periodic boundary condition was for a different test problem. And you'll see why momentarily. So this is our electric field. This is the driver, right? We're going to drive through the electric field on the boundary. This is just the components that we've chosen to use. This will generate the magnetic field, right, this way and with our particles, right? Our particles drift out of the plane, and this reinforces this magnetic field out of the plane as well. So we decided to take just a center region of the domain and shear it. So magnetic field component is out of the plane on this side and in the plane on the other side, right? So it's oppositely signed. Right. There's our profile. And we drive it, in this case we drove it for 2 alphane times. And what we're looking at here is the magnetic field out of the plane, which is strong here, and the magnetic field in the plane, which is weaker through here. The color bars are not actually great. And so this kind of looks like what we had expected because these field lines are tied. And so you see this, this is round, right? If this was stronger, you would really see the field lines bulged. And this is what our current densities look like. This is J in the plane, along the field. And this is our current out of the plane, which is very, very weak. But I chose this for a reason because you can just start to see these little bits forming here and here. And you can see them here and here as well. So for like half a second, everything looked like it was working just fine. And then disaster. Right. This, whatever these horrible waves are, just completely destroy everything. And you end up with just this, diffusive kind of mess throughout the domain. And we thought, oh no, what are we going to do? Where are these waves coming from? Clearly, these closed boundaries are a problem. You really can't just reflect particles. They really do have to be able to flow out. Yeah. So what we're trying to do right now is to implement open boundary conditions in PSC and hope that this fixes the problem. If this doesn't fix the problem, I don't know what we're going to do. We'll have some other moment of inspiration, I'm sure. Yes, you have a question? I see a puzzled look.
Always have a puzzle. Okay.
You have diffusion in your model?
Not explicitly.
Okay.
Yeah. All right. Okay. So that's kind of where we're at. We're trying to do new things in all kinds of regimes by examining these charge imbalance current sheets, which are really cool for kineticists, by driving reconnection with a shear driver. So reconnection in these current sheets impacts global evolution for both types of star systems. Right? We're very familiar with why this is important in the sun, for the sun. The pulsars. These pulsar flares, I got to study these a little bit more. I just love this concept. Current sheets don't just exist, right? I mean, they formed in a pulsar too. So I'd like to know how the pulsar current sheets actually form, from the beginning of the life of a pulsar. So where else in the cosmos might kinetics be important? That's kind of always what I'm thinking of. Yeah. Okay, so that's my presentation. Yes, do you have a question?
Any questions?
Yeah, I'm starting to wonder what other, because you introduced this as, in terms of stars in general, I thought.
Other stars. What other
Applying
stars?
it to other cool stars, or?
At the moment, just these two. But I'd be really fascinated to study other types of stars as well. Yeah. Do you have thoughts? No? Oh, okay. Okay.
Of course, everybody's trying to understand dynamo theory and sort of stars in general.
Yeah, it's good stuff. It's really cool.
So has there been any other codes, PIC codes that implemented outflow boundary conditions?
Oh, yeah. Bill Daughton's VPIC has open boundaries. Right, so it's tractable, it's doable. Okay. In fact, Naoki Besho also has open boundaries in his XPIC code, which I would use, except it's not as nicely parallelized as PSC. It's not optimized for large systems.
Right, so you have to constantly introduce new particles and let some particle go out.
They flow out, right. Yeah.
So what if sometimes that suppose like you form islands and then they collapse into one space unit and then you're not very well sampled in phase space anymore. So what do? You introduce more particles or so that it's better, or it's always the same?
Not so that you don't want to introduce more particles just so that they accurately represent phase space, right?
I mean, in different space. I mean, you're trying to.
Okay, there's a very nice set of conditions that Bill Daughton shows in his paper, which says that, across the boundary, the first three moments of the distribution function, the gradient of the first three moments of the distribution should be 0. So this feeds in enough particles. This is another tricky bit with the PIC codes is that you will lose particles really, really fast if you don't replace them. So this feeds in enough particles that you can keep your simulation going and should, I believe, although we haven't studied this yet, when you have at the inflow region, where your fields start to collapse this way, you should actually feed in more particles this way. And I think that happens naturally with these boundary conditions.
Right, you drive the electric field and
it will come in. You're right, they will come in. And you have a few that come in through the outflow boundaries as well, but not as many. Yeah.
more questions? So you'll be around for
Today, I'll be around
Okay.
tomorrow if people want to talk too.
Okay. So she is sitting in the colloquium speaker's office. So if there's no more questions, any more questions? Okay, let's thank the speaker again.